transformations unless the radius of the ball is smaller than this number r, which is here. Okay. This seems to be in conflict with the usual interpretation of Liouville's theorem. Okay? Because Liouville's theorem says that Hamiltonian flows or symplectomorphisms do not change volume, but not changing volume does not mean not changing shape. So say, perhaps using symplectomorphism, specially constructed one would be able to transform this in a kind of sausage, so thrust it inside the ellipsoid. But no, it does not work. By the way, if you use general volume preserving diffeomorphisms, it's much easier. You can do it then. But symplectomorphisms, that is canonical transformations, are of a very special nature, actually. A variant of Gromov's non-squeezing theorem is the following. Take, and this will be very close to the uncertainty principle, take a plane of conjugate variables in phase space. That is a plane of type xj, pj, the same index, okay? These are called conjugate variables. Here. And consider, well, a ball, again, with radius r in phase space. Now, if I project this ball on the plane here, I will get a circle. Of course, a circle with radius pi r squared. This is obvious, okay? Suppose now that I start distorting this ball by using canonical transformations. For instance, the Hamiltonian flow. This ball can distort while keeping a constant volume, of course. But what is going to happen? Suppose that this is the distorted ball here. The projection, orthogonal projection of the distorted ball on this plane will always have an area of at least pi r squared. So in other words, the area of the projection will not increase. You can see this is a variant of the uncertainty principle, but in the classical regime. Okay. Because if I take another plane here, xj and pk, with j different from k, then the projection can become arbitrarily small. But again, here the planes play a totally fundamental role here.
Maurice, can I just ask if you're excluding all dissipated processes here? Are you?
Yes, I'm talking about Hamiltonian dynamics.
Oh, still,
no,
right.
Otherwise it's not true. No, I must have Hamiltonian flows. Yes, of course.
But still possibly non-linear.
Of course. But nevertheless, I mean, this principle puts, from my point of view, severe limitations on the possible chaotic behavior in Hamiltonian processes. You know, Penrose, in Penrose's book, The Emperor's New Mind, there are several pages about Liouville's theorem, and Penrose says more or less, yes, okay, Hamiltonian mechanics cannot be true mechanics, it does not apply to the real world, and then he gives examples just of terrible distortions, of course, of flows which are volume preserving. But of course, he could not know when the book was written that Hamiltonian diffeomorphisms have a very special structure. I mean, this principle, the almost non-squeezing theorem, was discovered only in 1985, so this is very recent actually. Nobody knew about that before. And I mean, the first citations of this in the mathematical literature appear only in the 90s. And in physics, I think there are very few people who have realized that this can be of some importance, really. And of course, well, okay, I'm not physicist enough to be able to judge whether this can have far-reaching consequences or not. But what I'm going to show today is that it applies very well to the uncertainty principle, which you can already see here. Okay? Good. So let's now turn to the uncertainty principle. Okay. I think that everybody knows what this is about. Of course, this is the naive version here, the textbook example you find in every books on elementary quantum mechanics here. It turns out that the sharp principle is this one here. I will explain what this is about. Because when you write this, you don't take into account the covariances. That is the correlation between the variables here. This form was due, I think, to Robertson and Schrödinger, actually, I think. It was very famous sources, but that Schrödinger had proposed this sharper version, which was then proven by Robertson in 1932 or 35 or something like that. Yeah. Okay, now, and here I'm taking a big shortcut. It turns out that this here is equivalent to something very algebraic, where the standard symplectic matrix J intervenes. What is sigma? Sigma is what is called the covariance matrix. I'm going to define that in a few seconds. And this inequality is equivalent to this inequality. This means that sigma, covariance matrix, plus I h bar over 2j is a positive semi-definite matrix. And this is the symplectic formulation, or one symplectic formulation of the uncertainty principle. It turns out that this is equivalent to saying that the phase space ellipsoid, defined by this relation, has symplectic capacity superior or equal to 1/2 of h. That is, it says that we cannot squeeze a ball with radius smaller than square root of h bar inside this ellipsoid. This is the so-called Wigner ellipsoid, which is immediately related to the Wigner transform, as we will see. And being related to the Wigner transform is related to Bohm mechanics. Well, that's a shortcut, I know, but that's it. But nevertheless. Okay.
But where does the symplectic form come from here? We are in quantum mechanics now, and
Well, it comes from the fact that we have a phase space. Some physicists of the older school talk about mock phase space. They don't believe in phase space in quantum mechanics, but all young people like you, for instance, you know that quantum mechanics makes sense. I mean, phase space makes sense. I'm talking about the phase space formulation of quantum mechanics. The Wigner-Royal formulation. I mean, I understand that physicists can say, ooh, there can be no such thing as a phase space in quantum mechanics. Mathematically, it can be, and actually, you can calculate in phase space quite abstractly as much as you like. There's no problem with that.
well, you say that the precise form of
Yeah.
the uncertain relation is equivalent in
Uh-huh.
mathematical sense to this
Sure.
expression there. Well, the first is something about expectation values of operators. What is that?
I'm going to precise what I mean by this.
Okay.
Let me see. I did not actually invent this expression. It's commonly used in quantum optics. It's commonly used in quantum optics, and quantum optics is a part of quantum mechanics, I think. You know, in quantum optics, they have no problems. No. They have no problems using this in the study, especially in the study of entangled states. This is very, very, very common, because the covariance matrix plays, of course, a fundamental role in this thing. So let me talk a little bit about operator theory, so you will see where this comes from. Good. So how do you prove this? You see, perhaps we have to remember how one proves the usual uncertainty principle. Okay. You know that the usual uncertainty principle is a consequence of non-commutativity. I know that non-commutativity is very fashionable nowadays. I mean, it's not a... it's not a...
You almost sound like you disapprove.
It's obvious that non-commutativity plays a crucial role. I mean,
You know, it was the tone of voice.
okay.
The multiplication of covariance matrices is maybe non-commutative.
I don't know. No, it is commutative. No, I'm joking, of course. No. Okay, so let's take a